Welcome back to Discrete Math. Today we're going to talk about integer representations and algorithms. To begin with, let's review base 10. Suppose I give you some number 2237. This represents 7 plus 30 plus 200 plus 2000. Which we can write as 2 times 10 cubed plus 2 times 10 squared plus 3 times 10 plus 7. More generally, if AK minus 1, A2, A1, A0 is decimal representation of a number, then we can rewrite this as AK times 10 to the K plus, well, we have A1 times 10 to the 1 plus A0. What do you do in other bases? Let's look at base B. So this is a very general case. Let some number n be a natural number. Then its base B representation is AK, A1, A0 is all of this if the number n is equal to AK b to the k plus A1 times b to the 1 plus A0. And here we're assuming that these digits are appropriate digits in base B, which means they go from 0 to b minus 1. So in, for instance, base 10, if b is equal to 10, the appropriate digits are 0 through 9. If base b is 2, then the appropriate digits are only 0 and 1. Let's do the same thing, but instead, let's use base 3. What's the highest power of 3 that goes into 18? Well, 3 cubed is 27, so that's too big. 3 squared is 9. But you get 2 of those. And you'll have 0 times 3 to the 1 and 0, which means that the base 3 representation is 200. How about base 4, 5, 6, 7, and 8? Let's see, the biggest power of 4 that goes nicely into 18, not into, but that we can fit inside of this 18 is 4 squared. So 1 times 4 squared. 4 squared is 16. That leaves 2 left over. You can't subtract any 4s out of that 2. So you have 0 times 4 to the power 1, and then the 2 that you have left over. So the representation in base 4 is 102. Well, how about base 5? 5 squared is already too big. You can fit 3 5s in there, though. So 3 times 5 to the 1, that leaves 3 left over. And so we get 3, 3 in base 5. How about base 6? Again, you get 3 6s that go into this number, 3 times 6 to the 1, with nothing left over. So you get 30 in base 6. How about base 7? You can fit 2 7s in there. 2 times 7 is 14. You have a remainder of 4. So 24 base 7. 2 8s. That would be 2 times 8 is 16. That would leave 2 left over, so 22 in base 8. There's an important aspect of this representation of numbers in different bases that we need a theorem for. Choose your base to be a natural number bigger than or equal to 2, and let n be some natural number. Then n may be uniquely expressed as a k b to the k, a1b to the 1 plus a naught, which is the representation ak, a1, a naught in base b. So, n may be expressed this way means there exists a way to do it. Uniquely means there's only one way that this can be done. So every number has a unique base b representation. The proof of this theorem requires the use of something called math induction, and we haven't talked about that, so we'll have to defer the proof for a later time. Let's do some of these conversions the other way. Convert the following number 101101 in base 2 to base 10. Let's first express this number in base 2 as a sum of powers of 2. You'll have 1, 0 times 2 to the 1, 1 times 2 squared, 1 times 2 cubed, 0 times 2 to the 4th, and 1 times 2 to the 5th. Now, using our usual arithmetic, this is what? 32 plus 8 plus 4 plus 1. So that's 45. So there's the representation in base 10. We can see that because we'll have 4 10s and then 5. So this is the base 10 representation. Instead of base 10, let's convert this to base 3. We already know it's 45 in base 10. How many powers of 3? What's the highest power of 3 that goes into 45? And that would be 3 cubed. That would be 27, but only one of those fits. 45 minus 27 is what? 18. So how many 3's go in here? Well, 3 squared does twice. And so we get 1, 2, the powers of 3 to the 1. We get 0 of those, and we get 0 constants. So in base 3, it will be 1, 2, 0, 0. There are two very important number representations, very important bases that are commonly used in computer science besides base 2. Of course, base 2 is used, but so is octal, which is base 8, and hexadecimal, which is base 16. So base 2, base 8, and base 16. As an example, suppose we have the number 235 that is in base 8. What is this number in base 10? Well, it's in base 8, so it's going to be 2 times 8 squared plus 3 times 8 to the 1 plus 5. Well, 8 squared is 64, times 2 is 128. 3 times 4 is 24, plus 5. We'll have 140, 152, 157 in base 10. In base 10, we have 10 possible digits, 0 through 9. In base 2, your digits can only be zeros and ones. In base 16, you need 16 symbols for representing a number. Yeah, 0, 1, 2 to 9 gives you 10 symbols. So you have to append to this 6 more symbols, and those are going to be A, B, C, D, E, and F. So your digits can only take on these values. Here's an example. Suppose I have a base 16 number 2AE. Let's convert this to base 10. This is 2 times 16 squared plus A times 16 to the 1 plus E on top of that. Well, 16 squared is 256 times 2 is 512. A is the 10th symbol, so this is going to be 10 times 16, which is 160. So what symbol is E? We have 9, 10, 11, 12, 13, 14. So that's 672, 82, 686. There is an algorithm for general base conversions. And it goes like this. Suppose you have some natural number n, and b is also a natural number, but the base is at least 2. Then what you're going to do is you're going to divide n by b. And when you do, you're going to get a quotient and a remainder. That remainder is going to be the units place in your base b representation. After that, you take your quotient and divide that by b. We'll set our A1 to be R1. And we keep going until there's nothing left to divide. As an example, suppose we want to convert the number 213 in base 10 to hexadecimal, affectionately referred to simply as hex. This is base 16. So the first thing we need to do is we need to divide 213 by 16. How many times does 16 go into 213? We know it goes in at least 10 times, because 10 times 16 would be 160. But in fact, it goes in a few more times, 13. What is 13 times 16? Well, it's 18. We have 3 plus 1 is 4, and then 6 and 1. So it's 208. So the remainder here will be 213 minus 208, and we get then a remainder of 5. So 5 is going to be the first digit. Notice that we have left over this Q0, which is 13. That's smaller than 16. So what is the 13 symbol in hex? Well, we have 0 through 9. 10 would be A. 11 would be B. 12 would be C. 13 must then be D. So the representation in hex is D5 in base 16. We're going to consider conversions between binary, octal, and hex. We're going to see that these will have certain efficiencies based upon the fact that it's all based on powers of 2, whichever way you go. So for instance, 8 is 2 cubed, 1 times 2 cubed, and so we get 1, 0 in the square, 0 in the power 1, 0 in the units place in base 2. What about 16? Well, that's 2 to the 4, so in base 2, that's 1, 0, 0, 0, 0. Like that. For example, so what is this same number in base 16? Remember, 16 in decimal is 1, 0, 0, 0, 0. So 4 zeros. 0, 0, 0, 0, 1. So that's where we're going to have 1, 1, 0 16s. So how many 16s is 1, 1, 0? Well, this is 2 squared, that's 4, plus 2 is 6. So we're going to have 6 of these 16s. And then what's left over is the rest of this, 1, 1, 0, 1. This is 2 to the 1, 2 squared, 2 cubed, that's 8, plus 4, plus 1. So that's 12 plus 1 is 13. What is the 13 symbol in hex? Remember, you have 9, the 10 symbol is A, the 11 symbol is B, the 12 symbol is C, and the 13 symbol is D. So it's 6D in base 16. Let's see if we can convert 27 in base 8 to binary. So this is going to be 2 times 8 to the 1 plus 7. Well, 8 is going to be 1, 0, 0, 0. And we're going to have to double that. If you double that, you end up with, well, this down here. 1, 0, 0, 0, 0. What is 7 in binary? Well, it doesn't have any 2 cubed, so it's 2 squared. That's 4, leaves over 3. So that's going to have another 2 and another 1 after that. So we'll have 1, 0, 1, 1, 1 in binary. Next, let's convert A3 in hexadecimal to binary. Notice this is A times 16 to the 1 plus 3. A is the 10th symbol. So we'll have A times 16 to the 1, 16 to the 1 being this. So we're going to have 10 times this. What is 10 in binary? 10, base 10, corresponds to, we have 1, 2 cubed, so that's 8. 0, 2 squared, 1, 2, and 0. So this is 2 to the power 3, that's 8, plus 2 to the power 1, that's 10. So base 10, you get 1, 0, 1, 0. So I'm taking this 1, 0, 1, 0 and multiplying it by this 1, 0, 0, 0, 0. So that's going to give me 1, 0, 1, 0, 0, 0, 0, 0, and on top of that we have a 3, which is represented by 1, 1. So altogether we're going to have 1, 0, 1, 0, 0, 0, 1, 1 in base 2. Next, I want to look at how you add numbers in various bases. Let's start with base 2. And remember, here your digits only take values up to b minus 1. So in binary, your digits can only be 0 or 1. 1 plus 1 is going to be a 10. You'll have to carry a 1. So 1 plus 0, 0 plus 1, 1 plus 0, 1 plus 1 is, we'll have to carry a 1 over here. And so this will be the sum. Let's do another example. 1110 added together with 1111. Well, 0 and 1 is 1. 1, 1, 0, carry a 1. 1 plus 1 gives you another 1, carry a 1. And then 1 plus 1, another carry a 1 as well. And so there's your sum. So how do you add numbers in base B? Let's suppose we have numbers in base B with these representations. Let's suppose that they have the same number of digits. And we're trying to add these. The first thing you would do is you would add A0 plus B0. And you would convert that to base B, because this may be, if this is 1 and this is 1, you get 2. That's too big. If you're in base B, you should be rewriting this as Q1 times B plus R1. But we're going to denote it a little differently. We're going to call this carry 1 times B plus the 0th digit of the sum. This is the one that you carry to the next sum. From there on, you're going to take these digits plus the carry. So it's going to be A1 plus B1 plus C1. And you want to represent that also in base B. So it's going to be C2 times B plus S1. And we'll keep doing this until we run out of digits. So we'll end up with SK plus 1, SK, S1, S0 as our representation in base B. You have to include this extra digit because of the possibility of a carry into this next column. Multiplication in binary will take a familiar pattern. Let's suppose we're multiplying these numbers. Then 1 times the thing above, shift over 1 times the thing above, and then add. Let's see if this makes sense, and does it really match what we would get if we converted everything over to base 10. Remember, this is 2 cubed plus 1 times 2 squared plus 1 times 2 plus 1, which is 8 plus 4 plus 2 plus 1. 8 and 2 is 10, and then another 5 gives you 15. So in base 10, we're looking at 15. 101 in base 2 is 2 squared plus 1, which is 5. So this represents the number of 5. 1, it's 2 to the power 1 plus 2 to the power 0, or just 2 plus 1 is 3. And yeah, 3 times 5 is 15. Let's look at an algorithm for div and mod. Remember, div gives you the quotient and mod gives you the remainder. Suppose we're looking for 7 div 2. Well, how many times does 2 go into 7? There are 3 2's that go into 7, because we can write 7 as 3 times 2 plus 1. So how many 2's do you get? There's your quotient. And consequently 7 mod 2 would be 1. There's another simple algorithm for calculating these things. Let's look at div first. Subtract 2, you get 5. How many 2's can you subtract? You can subtract another 2. That gives you 3. So you keep subtracting 2's. We have 3 2's that we subtract, and a 1 left over. So that gives you 1 as the 7 mod 2, and for 7 div 2, you get 3, because there are 3 2's that you were able to subtract. In cryptography theory, we often need to calculate a to the power n mod some number m. Note, if you have this number and you want to calculate a to the n plus 1 mod m, to do this, we take a times a to the n mod m, but then whatever this is, we calculate mod m. Let's look at fast modular exponentiation. And for this purpose, suppose we have some number n, which has a binary representation like this, and let's try to calculate b to the power of n. Then that will literally be b to the power of a k times 2 to the k plus a whole bunch of other terms terminating in the sequence a1 times 2 to the 1 plus a naught. And we know we can split this up into b times a k times 2 to the k times b times a k minus 1, 2 to the k minus 1, b a1 times 2 plus b to the power a naught. Oh, not plus, but rather times. Note, if any of these a's is 0, then b to the a j 2 to the j will be b to the 0, or just 1, a factor of 1. Those factors you can ignore. If we're assuming that this is in binary, then these digits can only be 0's and 1's, which means otherwise b to the aj 2 to the k will be b to the 1 times 2 to the k. So you really only have to know b to various powers of 2. Once you've multiplied the appropriate powers of 2, the next step is to take this mod m, whatever your number m is. So for example, suppose we want to calculate 3 to the power of 11. Because of our previous discussion, we should convert 11 to binary. So that's 3 to the power of 1011 in base 2. You can tell this because here you have 2 cubed. That's going to be 8, plus another 2, that's 10, plus another 1, that's 11. So according to our prior discussion, this should be 3 to the power of 2 cubed times 1 times 3 to the power of 2 to the 1 times 3 to the power of 1. So how much is that? Well, 3 squared, that's 9. What's 3 times 2 cubed? 2 cubed is 8. So it's 3 to the 8th times 9 times 3. So 3 to the 8, it turns out, is 6561. And if you multiply all these together, you get 177,147. Now, we're going to use this to find 3 to the 11th mod 5. So we need to calculate this number, mod 5. Well, mod 5 goes in there with a remainder of 2, right? And so 3 to 11 mod 5, it's easier if you first convert the 11 into binary. Use our special way of multiplying those factors together, and then do the simple arithmetic, then simply mod out by whatever your number m is.